Okay, so I'm just going to kind of walk through the PowerPoint. This goes right along with the notes, and then I'll also post the slides so you can kind of go back and fill it in if you need to, or you can just fill it in while I'm talking. So the last little part of this unit is about momentum, and you probably think when you think of momentum, you think of like, you know, oh, that person had a lot of momentum, or that car had a lot of momentum. And when you're thinking that, you're probably thinking, well, if something has a lot of momentum, it's kind of like, oh, well, it's going to be hard to stop that object, right? Like if you're thinking about, two football players running in for a tackle, whoever has the most momentum is going to be the one that wins that tackle, right? If somebody's moving really quickly, if it's a big dude, they're going to have more momentum. They might knock the other person down and keep going. So that's basically what we're talking about. Momentum is just the motion of some kind of moving object. So any moving object is going to have momentum. And it's related to the mass and the velocity of the object. So if the object is big, it's going to have more momentum than a smaller object. If the object is moving fast, it's going to have more momentum than the slower object. Okay, so that's just like why can a large football player run through a smaller player? Well, he has more momentum. Okay. We also have a formula here. So P is our symbol for momentum, and then we have our mass and velocity. And we get our momentum by just multiplying those two together. So let's do some problems real quick. So it says a 300 kilogram tiger has a velocity of 3. What's the momentum? So I'm just going to use my formula. P equals mv. It says my mass is 300. My velocity is 3. So when I multiply that together, I get 900. And then my units are this kilograms times meters per second. There's not really any kind of special unit for momentum. Okay, so that would be my answer right there. And these are on your notes. You can just kind of work through them as I go. I'm going to skip over number 2 and 3. You should be able to answer those based on what we've talked about so far. Number 4 is just a little different. It's more practice, but I just kind of want to show you what it's asking. So you're using this information for all of the A through D. So I'll show you what I mean with A and B. So A is just asking for the momentum of the car. So I'm going to use my equation, P equals mv. Okay, my mass is 1,000. My velocity is 20. So when I multiply those together, I get 20,000 kilograms times meters per second. Okay, so that is my momentum of the car. All right, so with B, what it's doing is it's saying, well, how fast would a 100 kilogram bicyclist have to go to have the same momentum? So my momentum is going to be the same as the car, that 20,000. Okay, so how could I plug that into my formula? P equals mv, right? Well, I have my momentum, 20,000. I have my mass, but I'm missing my velocity. So how can I get my velocity by itself? I just have to divide by my mass. So I end up with 200 is my velocity, meters per second. Okay, so C and D, you're going to do the same thing. You're basically just taking the momentum, dividing it by the mass to get the velocity. Okay, so it's just a little bit different type of equation. Okay, so when we're talking about momentum, one of the things we want to focus on is collision. So we know that a collision is just when two things bump into each other or collide. Okay, we're familiar with that term. But we may not be familiar with the fact that during a collision, right, momentum and sometimes kinetic energy is going to be conserved. So you can think about it like if you're standing still and somebody walks into you, right, they make you move, right? They're kind of pushing into you. It might make them slow down, but it might make you move the opposite direction. So that's what we're talking about when we're saying momentum's conserved. It's actually just being transferred from one object to the other. Okay, and we talk about collisions when we talk about forces, because just like if somebody runs into you, okay, they might be transferring their momentum. They're also applying a force to you. Okay, that's how we're kind of transferring this momentum, is we're applying forces to the other objects. Okay, so whichever object has the most momentum, that object will also have the most, it kind of got cut off, the most force, right? Which makes sense. If you're thinking about our football players running down the field, whichever player has the most momentum is going to be the one that's going to push through the line, right? Because they're applying the most force. So these two terms kind of go together. When we're talking about kinetic energy, okay, we need to know that it's the energy of moving objects. So everything that's moving has some amount of kinetic energy. So when we're talking about two things colliding, if they're moving, right, they both have kinetic energy. Okay, so that's kind of just so we know what we're talking about when we say the term kinetic energy is conserved. So these are just some examples down here. All moving objects, like we said, have kinetic energy. Sound is kinetic energy. Heat energy is kinetic energy. Those are all just examples. Okay, sound, because it's actual waves, right? That's why I can hear you from across the room. The sound is moving towards me. And then the same thing with heat. Why can I feel the heat from a fire? Well, because the heat is moving from the fire towards me. Okay, so it's moving energy. So when we're talking about collisions, there's actually two types, and we need to be able to tell the difference between the two. So elastic collisions, and you're just kind of filling this in along with your notes as we go. Okay, elastic collisions is basically just that two objects collide, they bounce apart. Okay, this is like a pool ball scenario. Okay, if you've ever played pool, if you've ever bounced a ball on the floor, like a bouncy ball, you know that it's going to bounce up, with this, depending on how fast it's moving when it hits the ground. So if you barely bounce it on the ground, it's only going to bounce up a little bit, right? If you bounce it hard, it's going to bounce up, pretty high. But it should bounce about the same height that you throw it or that you drop it from. Same thing with a pool ball, right? If I want the ball to go all the way across the pool table, I have to hit it with more amount of force. That ball has to be moving quicker with more speed. Okay, so in my elastic collisions, it's important to know that momentum and kinetic energy are both conserved. Okay, and we're going to show an example of that in just a minute. With inelastic collisions, the main difference is that these objects stick together. Okay, and when that happens, my momentum is conserved, but some of my kinetic energy is actually lost. Okay, and the reason that it's lost is doesn't disappear, but it's actually converted or transformed into different types of kinetic energy. So instead of just moving, right, instead of my kinetic energy being my motion, it's converted into sound and heat. So a lot of times what we're going to see is that our objects after the collision, they're going to slow down, okay, because they're losing that speed to heat and sound. And this kind of makes sense with car crashes, right? If two cars collide, they run into each other, a lot of times they stick together, and then they slow down, right? They're kind of losing some of that speed. So I think you might have to scroll back up in your notes just to get this definition, but the law of conservation of momentum is basically the same as all the other laws of conservation we've talked about. It's just saying that momentum's conserved. Okay, my total momentum of my system is conserved. And we actually have an equation that we can use to calculate that, okay, to show that that's really happening. So we're going to kind of look at an example here in just a second, that if a moving car hits a stopped car, what's going to happen to that stopped car? Okay, well, it's going to start to move because that first car slows down, maybe, right? Well, that speed has to be transferred to another object. So that car that was stopped, that's why all of a sudden it moves forward, right? Because it's kind of, that momentum is being transferred to the other car. Okay, and you can kind of think of it too. Well, that car's applying a force on the stopped car, right? So it's moving forward. That's why momentum and forces are kind of related to each other. You can kind of talk about them at the same time. So we're going to use this equation here with a little scenario. So all that my conservation of momentum law is saying is that whatever momentum I have before my collision, I'm going to have that same momentum after, even though it might be in different cars. Okay. So let's look at the example that we have right here. Okay, where you can see it. So this is my initial up here. Okay, this is like my initial scenario. So right now, this car is moving, my red car, at 5 meters per second towards this direction, towards my blue. This car is moving 5 meters per second in the opposite direction. And because it's moving in the opposite direction, we're just going to give it this little negative sign. It doesn't mean it's going slower than 0. It just means that negative is like a direction sign. Okay, it means it's going the opposite way of my red car. Okay, and then I can look at my mass. So my mass for my red car is 1 kilogram, and then my blue car actually weighs 3 kilograms. So all I'm going to do is plug this in, and this is my initial or my before. Okay, so for my red car, my mass is 1 and my velocity is 5. For my blue car, my mass is 3, my velocity is minus 5. And remember, that minus does not mean it's moving slow. It's still moving the same speed as the red car. It's just opposite directions. Okay, so now I can kind of look. This is after they've collided. So they've kind of bounced into each other. And what happens is this red car kind of shoots backwards this way. So we can kind of make a guess of why do you think the red car moved backwards, why the blue car stopped. Right? They're moving the same speed, but if we remember, the blue car is pretty heavy. Right? So basically all that happened, the blue car, even though it was moving, it's pretty heavy. So it kind of transferred all its momentum to the red car, because it's easier for the blue car to just stop. And then the red car kind of bounces away with a lot of speed because it weighs less. Okay, so when I'm plugging in my equations, my mass for my red car, right, is still 1 gram. I didn't change anything about my masses. My velocity, remember I have this minus 10. That's just telling me it's going in that opposite direction. Plus the mass of my blue car, which is 3, and the velocity is 0. Okay, so when I multiply this out, I get 1 times 5 is 5, plus 3 times negative 5 is minus 15, equals 1 times negative 10 is minus 10, plus 3 times 0 is 0. Okay, so remember when I add a negative number, it's just like subtracting. So 5 minus 15 is negative 10. Negative 10 plus 0 is negative 10. So what I've shown is in my collision, even though my cars may weigh that differently, they're moving different directions. At the end, one of them is stopped and one of them's going backwards. Their speeds have changed. My total momentum of the system has stayed the same. It's still, my momentum at the beginning was negative 10. My momentum at the end is negative 10. Okay. And if you think about it, it kind of makes sense that it's this negative, that it's pushing, everything is pushing towards this way, because the car that's pushing left weighs the most. So it's going to be applying the most force. It's going to have the most momentum going towards the left. My little red car is very light, right? It's only 1 kilogram. It doesn't have all these extra weights on it. So it doesn't have enough force to push through the big car or the big football player. You can think about it that way, right? If you got 2 people, they're running at the same speed towards each other, the bigger one is going to overpower the smaller one simply because the mass is bigger. Okay, you're applying more force, so your momentum is stronger. You do have, before I close it out, just to mention, there's a few questions, I think 3 questions, just based on what we've learned. If you need to Google to research a little bit, that's fine. But you should be able to answer those 3